Good afternoon and welcome to Crippling HTTPS with Unholy PAC. You are in Mandalay EF, and our speakers today are Isaac Kotler and Amit Klein. A couple of notes here. We need to stop by the business hall located in Bayside AB during the day and for the welcome reception tonight from 1730 to 1900. Also, the Black Hat Arsenal is on the Palm Foyer, Level 3. Finally, the Pawnee Awards are this evening, and they are in Mandalay Bay, BCD at 1830. We also appreciate everybody making sure that their phones are on vibrate. We don't need to hear your cool ringtones. And finally, there are microphones in the audience, so when Q&A time comes, please go to the microphone to ask your questions since these are being recorded. And with that, gentlemen, it is yours.
Thank you, Kevin. Good afternoon, ladies and gentlemen, to this Black Hat talk about crippling HTTPS with Unholy PAC. With us today is Isaac Kotler, who is the CTO and co-founder of SafeBridge, and myself, Amit Klein, VP Security Research for SafeBridge as well. Before we actually begin, I would like to give us a little teaser here and describe a situation wherein you're in a potentially malicious network. It could be a free Wi-Fi, it could be any guest network you plug in your computer to, or maybe your own corporate LAN through being compromised by an infected endpoint. So obviously you are a security conscious researcher, and thus you restrict yourself to HTTPS. Browsing to HSTS sites. I remind you that Google.com just enabled HSTS on their sites last week, or using any false TLS or SSL plugin in your browser. So theoretically, since all your traffic is encrypted from the first byte, you should be secure. But are you indeed? So the rest of the presentation will go along the following lines. We'll first discuss the PAC and WPAD. Then we will explain how we can steal HTTPS URLs over LAN or wireless LAN and why this is scary. Then we'll describe another concept, a related concept called PAC malware, and we'll explain the capabilities of the PAC malware and describe the CNC protocol. We'll also show a PAC feature matrix wherein we'll correlate the virus browsers versus the PAC features, and we'll conclude with ideas for remediation and fix. So, PAC refresher. A PAC is an acronym for proxy autoconfig. It's a file that designates for the browser which proxy to use for each and every URL that the browser is about to navigate to. It's a JavaScript base, so the logic is JavaScript. And the API between the browser and PAC is the find proxy for URL function with two arguments that the PAC needs to implement and the browser needs to invoke per each URL. This is a textbook example for PAC file. It's a very simple one. As you can see, it implements find proxy for URL. The browser needs to invoke this function with a URL and just the host part for the second argument. And what this function does in this case is do a regular expression match between the host and example.com. And if the match succeeds, it returns direct, which tells the browser not to go through a proxy. However, if the regular expression does not match, the PAC function, the find proxy for URL, returns a series of proxies to be used in the format of proxy name or IP colon port, semicolon separates those entries from each other, and the logic is that the browser needs to fall back from the first one to the second one until the last one, and direct tells the browser to use a direct connection, i.e. not through a proxy. What is available to the JavaScript code in the PAC context, in the execution, while the browser executes the PAC logic. It has no window object and it has no document object. So all the DOM functions you are so used to and love for example, in cross-site scripting payloads and HTML games and attacks are not there. For example, no XML HTTP request, no loading of additional code via script injection, no hitting external resources via IMG injection, and so forth and so forth and so forth. All these simply are not there. What is there, apart from the built-in functions and objects like math and like eval, are a set of about a dozen functions that are specific to PAC and we group them into a binary function like DNS domain is in net, and so forth, not too helpful. Weekday range and date range and time range that help the coder to do some date and time based logic, and shell expression match, the general regular expression engine. DNS resolve and is resolvable, which are more interesting in our context, and they can do the logic is self-explanatory. It can either resolve into IP address or just tell us if a hostname is resolvable. My IP address is simply the IP address for the current machine. And alert, which is a non-standard implementation in a browser, may display some message as a pop-up. And where does the browser obtain the PAC file from? The browser has, by configuration, two options to retrieve a PAC file. One is the manual PAC file configuration, in which case the browser, one has to tell the browser the URL for the PAC file. And the other one is the more automatic way or fashion of obtaining a PAC through another protocol called Web Proxy Auto Discovery, or WPAD. At the right-hand side of the screen, you can see a screenshot from Windows system configuration, wherein the checkbox for using WPAD, which is called in Windows jargon automatically detect setting, is marked. In this case, it is not. In this case, it is not checked. So the machine here is not configured to use WPAD. But if you check this box, the machine will use WPAD. And so we need to discuss WPAD. So as we said earlier, it requires a specific checkbox checked in the browser. It is, in fact, quite common in enterprises. And in Windows at large, it is the default, at least for Windows 10. We checked that. Probably for earlier operating systems as well. And the way WPAD semi-standard works is that it provides the operating system or the browser with a set of fallbacks to find the PAC, to find the PAC, or set fallback options to find the PAC. The first priority is using DHCP. It works only for IPv4 networks, and the idea here is that during DHCP handshake, the DHCP server provides DHCP data, which is called options, to the client. And one of those options, option 252 to be specific, designates the PAC URL that the DHCP wants the client to use. If no DHCP handshake, no DHCP exchange took place, or no option 252 is present in the DHCP options part, the browser and operating system fall back to the second option, which is using DNS, and in which case the browser and operating system issue a DNS query for wpad.domain, where domain is the present domain that the browser or that the operating system is configured to use. If this hostname is resolved into an IP address, the browser with an operating system will then issue an HTTP request to the said IP with the resource requested /wpad.dat. This is a hardwired string. And whatever comes out from this request will be the PAC file. This scheme, this WPAD, is supported by Windows and Mac. We've seen it working well with Edge and Internet Explorer and Firefox, Chrome and Safari. WPAD is not supported by iPhone and Android. So now that we laid the background for the first concept, we move to describe this in part 1, and the concept of HTTPS subversion with malicious PAC. And the main idea goes as following. We first the first thing, the context is the scenario in which a malicious actor in your public Wi-Fi or your corporate LAN has access. The malicious actor resides on the LAN. It has access to the LAN. What this malicious actor needs to do is to force the browser to use a malicious PAC. And how would the malicious actor go on doing that? If your operating system engages, once you plug in your laptop to this LAN, your operating system starts a DHCP negotiation to get DHCP parameters. The malicious actor needs to spoof or hijack this DHCP traffic and provide its own DHCP response containing an option 252 pointing at the malicious URL for PAC. If your operating system reverts to using DNS, then again the malicious actor needs to spoof or hijack the DNS traffic and provide an attacker IP for WPAD queries. The browser then requests the PAC from the attacker's IP or URL, and now the browser has the malicious PAC. The browser exposes the HTTPS URLs to the PAC to the function find proxy for URL. It's important to stress that this is not an attack against TLS or SSL. The URL is intercepted before it is serialized as HTTP and encrypted in TLS or SSL. So TLS or SSL versions or features or configuration are simply not relevant and will not help to mitigate this attack. So once the malicious PAC logic obtains the URL, the HTTPS URL, the final step is to exfiltrate this URL to an attacker server. Because right now the PAC file is running in the context of the victim browser. It's still on the victim operating system. We need to exfiltrate the URL to the attacker machine. And the attacker does that by employing DNS resolve or is resolvable. And that these functions actually go and do DNS resolution, and so they can touch outside external servers. The attacker can do that by chopping the URL into small chunks that can fit in a DNS query and appending an attacker-owned domain like attacker.com to the hostname and then invoking, say, DNS resolve. This will cause the DNS query to arrive eventually at the authoritative name server for attacker.com, which can be the attacker's DNS server. And the attacker DNS server needs to collect all those queries and deserialize them, serialize them back and deserialize them into the single URL, and thus the attacker obtains the exfiltrated URL. Here's an outline of how a malicious PAC may look like. You can see at the bottom right part of the screen the function find proxy for URL that the browser invokes. To clarify, we split the exfiltration and the actual functionality. So first the function, the find proxy for URL invokes exfil send with the URL, and that exfil send, as the name hints, takes care of the exfiltration, and it returns a direct string telling the browser to use a direct connection. And the exfil send is the workhorse here. Without going into details, what it does is hex encoding each and every byte of the data, the URL in our case, chopping it to slices that can fit a DNS query, adding the attacker domain at the end, and invoking DNS resolve. Interestingly enough, if you look at the first line of the right-hand side screenshot, you see that DNS resolve, which is used to exfiltrate, and interestingly enough, you will see us adding an empty string to it, and we'll touch that later. There's a lot of machinery here that needs to be implemented in order for the protocol to be resilient and to be fully operational with long URLs and URLs that contains various characters and so forth. You'll have the full implementation in our Git repository, whose URL we'll provide in a later slide. Now that we have HTTPS URLs, what can we do with them? So HTTPS URLs are very interesting. They may contain very sensitive information. Think about services that are used to share files or resources between users. The way a first user shares a file or resource with a second user typically involves having the service either automatically or manually send an email to the second user that the first user wants to share the resource with. And that email contains a single URL that once clicked allows the second user access to the resource with privileges assigned by the first user. Now let's say that the second user has this malicious PAC loaded to the browser and the URLs exfiltrated to the attacker. The attacker now obtains those URLs and can put them or can navigate to them with a browser and obtain the same resource, the same file with the same privileges as the second entity. OpenID is another very interesting case because OpenID in the last phase of authentication redirects the user's browser from the authenticator site to the service site, and it does so by providing a URL redirection to the service site, to the site that needs the authentication, with some token parameters, the query parameters that tells the service side that the user is indeed authenticated and is allowed to use the site. Again, malicious PAC file in the user's browser can exfiltrate this URL to the attacker, and the attacker can write the same session with the user with the same set of privileges. Password reset is, of course, another lovely example wherein the URL can be stolen from the user, and the attacker can not only access the account, the attacker can also lock out the genuine user by choosing the attacker's password before the user manages to click the URL, and so it's even more powerful in such cases. Also keep in mind the scenario where URLs can have username and password as part of the URL before the hostname, like the https://username:/password at hostname. This is applicable to HTTP and HTTPS as well as for FTP, although we need to note that for FTP and HTTP, not HTTPS, this kind of credential theft is an optimization because the the malicious PAC file can simply direct all traffic to the attacker's proxy server, in which case plain text traffic like HTTP and FTP already contain those credentials, and thus the attacker can obtain those credentials even without URL exfiltration. However, this is a very inefficient way of doing so because passing all traffic through a proxy is CPU consuming, network consuming, and may flag the attacker's activity to any anomaly detection logic that exists on the network. We need to note that the concept of malicious WPAD pointing at a malicious PAC was discussed by the respectable researchers from NetResearch and Positive Security earlier. However, what they describe is just routing the whole traffic through a malicious proxy, which provides access to HTTP traffic and FTP traffic perhaps, but not to HTTPS traffic, because HTTPS traffic is encrypted before it arrives at the proxy. There were some mentions of this concept of URL exfiltration through a malicious PAC. It was very briefly mentioned in an answer by Leonid Evdokimov in Stack Exchange, which was published during our own research to the matter. It was described very briefly in an MSc thesis that was published in May 3rd after our own submission to Black Hat by Nicholas Golbovich, as well as a blog by Maxim Andreev about this concept back in June, again, while we were researching this topic. Unfortunately, this blog was in Russian, so we couldn't really find it. By the way, Maxim presents in parallel to us, so good luck to Maxim on this in his presentation. All those prior art cases did not really expand too much on this concept. We did. We provide full weaponization of this concept, including supporting long URLs, multiple messages, and multiple clients. We describe a two-way protocol from the PAC, from the malicious PAC to an attacker server. We provide open source and free code that implements all what we talk about. We also discuss a related additional concept called PAC malware. We provide a PAC feature matrix, and we provide all this in English. So let's see the ingredients that the attacker needs in order to implement this attack. So in order, the attacker needs some way of spoofing DHCP responses and or DNS responses. The attacker then needs to provide a web server to serve the malicious PAC. And then the attacker also needs the attacker's own domain controlled with an authoritative DNS server as a command and control server. The most important piece in this scheme is the uplink or the exfiltration protocol. The DNS and the attacker, so first let's see some basic concepts. For DNS suffix, the attacker needs a DNS suffix that is owned by the attacker. We call it suffix. Each browser needs to have its own unique ID, so we can split traffic between browsers. We call it client ID. This unique ID can be random, and indeed this is how we implement it. And then each message within a browser needs to have a unique ID that can be incremental, which we call message ID. Having this, the definition of the protocol is as following. First we hex encode the string that we need to exfiltrate. And this is not so sufficient. Obviously, we can use other schemes to encode it in a more sufficient manner, but we leave that for additional research. Then we break the message into fragments up to 63 characters because DNS labels are limited to 63 characters. Then every 3 or 4 fragments will fill a DNS query, but we need to keep the total length less than 253, which is the DNS limit for a host name. This forms a chunk, and we assign the chunk with a chunk ID number, and then we exfilter the chunk via DNS query. So the format, as you can see, is as following, and the last chunk is prepended by X to mark the end of the message. It's demo time right now, Itzik, so...
Okay, thank you very much, Amit. So we will present now a demo on how we are basically going to infect a Windows 10 machine using the DHCP method that Amit just described. So as Amit has explained, there's a couple different ingredients in order for us to align this attack. The first one is that we need to run a DHCP service which is going to offer the opcode 252, and as you can see, as I'm highlighting right now on my screen, it will basically serve the Windows 10 machine with this option pointing to this URL. Obviously, we need to run the DHCP service. We're going to have a very simple web service that will basically serve the malicious PAC file to the machine. And we have our command and control malicious PAC ready for action. So here's a very vanilla installation of Windows 10, and we have using Chrome version 51. And basically what I'm going to do now is I'm going to switch the machine to the malicious network. And I'm going to renew my my DHCP. As you can see, I've served the machine with the DHCP. The machine already accessed my web server, and I have hit on the proxy PAC file. And as you can see, also requests are starting to come in. So here's our interactive malware. There's a couple of very basic commands, and we'll show them during the demo. Right now you can see that there is no URLs that have been captured. Opening this Chrome version 51, Let's do a very basic surfing to a Placket website. Let's go into an HTTPS URL. As you can see, everything is very normal. There is no change in the UI, but at the same time, going back, you can see that all these different URLs have been captured. Now, as Amit described earlier, if you are using single sign SSO links or tokens within these URLs, let's make this one up. Basically, our malware also has a functionality to search for it. Sorry? So again, we can target and using our proof of concept malware to extract different tokens and different parameters which are being sent in the URLs. Amit, back to you.
Thank you, Itzik. So we're responsible researchers, so we need to tell you the fine print. First, the existing WPAD problem. If we're attacking a network that serves typically WPAD resources already, then we need to incorporate the genuine WPAD logic in our own malicious logic. We can do that by first capturing the genuine WPAD before the attack, and then incorporating the original fine proxy for URL, maybe adding a prefix or suffix so that it will not be it will differentiate it from the find proxy for URL function that we are about to code. And in our find proxy for URL, the last step is to return the calculation made by the original find proxy for URL to the browser. Another case that we need to consider is when we force a network that does not have WPAD or force a browser that's connected to a network that does not have WPAD to use a WPAD. In this case, Internet Explorer makes us face a problem, because in Internet Explorer, if it is configured to use a proxy in general, and WPAD is definitely such a configuration, and a site is one site is, or some sites are exempt from being proxied, which is the case when WPAD returns a direct directive, then those sites are automatically considered by Internet Explorer to be in the intranet zone, which is a problem, because from the sites that are in the intranet zone have their cookies container residing in a different location than sites that are in the internet zone. So whatever the user was used to in way of cookies and so forth will no longer work when the site is now considered in the intranet zone. So it has some user experience problems. Also, in some Internet Explorer versions, there is a visual indicator when a site is considered intranet zone. So we want to avoid this problem. One way of avoiding it is to just to return a proxy value for each and every URL for which find proxy for URL is involved. Obviously, a non-optimal situation, but much better than interrupting or impacting the user experience. As mentioned earlier, the URL interception quality varies among browsers. In Chrome version up to 51 and including, and in Firefox, the interception quality is good. Firefox actually didn't check 48, which was released yesterday. And in Chrome 52, which was released 2 weeks ago, they addressed the problem. In Internet Explorer and in Edge and in Safari, the URL interception quality is pretty bad. That is, the URLs are trimmed. I'll touch that in a later slide, and thus are almost useless to us. HTTPS and HTTP authentication credentials, those credentials that come before the hostname with the @ sign, are only intercepted in Firefox, and FTP credentials are intercepted in Firefox, Internet Explorer 8, and Safari. The uplink, as we said, is limited to 100 bytes per DNS query, so this is unoptimized. We can probably squeeze almost 200 bytes if we do it right. And then the protocol we designed does not handle packet loss and latency issues. We can probably add some TCP-like functions to it later. It's another topic for further research. As for the downlink, it will be described in part 2, and we will just hint that we use the eval function for maximum flexibility. To summarize this part of the presentation, I think what we've demonstrated is that the common belief that HTTPS traffic is secure even when used in hostile network is refuted with the WPAD scenario. What we've demonstrated is a way to bypass HTTPS, at least for URLs, providing access to HTTPS URLs. Obviously, it only works when the browser and the operating system is configured to use WPAD. It assumes that the attacker has access to the local network, and the interception quality is browser specific. We also showed that the HTTPS URLs can carry sensitive information like credentials or access tokens, and we touched the topic of FTP credentials. Now we're moving to part 2, the PAC malware. It's a related but somewhat different concept. And the main idea of PAC malware is that we have temporary access to the machine. It's not a remote attack, it's a local attack. And that can be achieved via malware running once on the machine and then deleting itself, or manually, but by someone having temporary access to the machine. And it turns that in Windows, all you need to do in order to configure a machine or a browser to use to use PAC is to set a registry key, a single registry key. The PAC URL, unlike WPAD, is supported by iPhone and Android, at least in version 5.0 and above. Interestingly enough, the PAC URL can be designated by a file scheme, in some browsers at least, and all of them, of course, support HTTP or HTTPS schemes. The file scheme can be UNC or local file. Also, for HTTP or HTTPS, that the resource or the host can be local, in which case the malware may want to install its own web server to serve the PAC, or it can be a remote destination. Unlike the remote attack, a local attack can also tweak the registry so that Internet Explorer will not use unproxied, will not assign unproxied destinations to the intranet zone. And more interestingly, it is possible to tweak the registry so that Internet Explorer will report each URL in full. And we mentioned earlier, Internet Explorer trims the URL so that they are useless. But if you have access to temporary access to the machine and you can change this registry key, Internet Explorer will start reporting full URLs. Some financial malware, which sometimes called bankers, do install malicious PACs as malware, but they do so in order to route the traffic, all traffic, to their own proxy servers. And as we said earlier, this will provide access, this will grant access to the attacker to HTTP traffic, but not to HTTPS traffic. So what are the PAC malware capabilities? Like I said, PAC can be installed as local file or UNC file, or if we're talking about HTTP or HTTPS, either on a local machine, but then you also have to install a web server, or on a remote URL. It is capable of intercepting URLs. We can establish a two-way link, uplink and downlink, over DNS queries. We can use the alert messages to display social engineering pop-ups. This works only in Internet Explorer. We can use eval for maximum flexibility. And here's the thing. If you have a two-way CNC protocol, the browser, or the PAC logic actually, can request data from the CNC server. Now, in order to provide maximum flexibility, the PAC file can download data from the CNC server and then invoke eval on this data so that this data actually is interpreted as code. And this provides maximum flexibility so that one day the PAC malware can do this, and an hour later it can do that, all using evil and flexible JavaScript code that is downloaded from the CNC server. One important feature for PAC malware that is of interest is that the possibility to route data to a proxy. This can be used for DDoS against a remote site. You can designate the site by IP address or by port, or we can use a denial of service. You can use it as a denial of service locally against specific sites. For example, we can route download or update.yourantivirushere.com to an IP address which does not return any value or any response, thereby effectively denying access from the local machine to those sites. The downlink protocol comprises of 3 bytes out of the 4 returned from a DNS query, and so messages can be numbered, and then the message length is obtained by resolving length.messageid.suffix, returning 3 bytes, designating the message length, and then consecutive 3 bytes of the message can be obtained by looping through them and requesting number.messageid.suffix. And a second demo by Itzik, please.
Thank you, Amit. So we're going to demonstrate right now some of the features that Amit has discussed about this malware capability. I'm going to attack right now the default Firefox that is coming with Ubuntu 16.00. The way we're going to implement this attack is I'm going to create a man in the middle. To make things easier, I've configured this machine DNS to basically be the server of the PAC malware. And of course, again, we're setting up a small web server to serve the PAC file itself. So right now, what we're going to do is we're going to fire up Firefox and then configure it to use the definition of the automatic proxy. So let's do that. Switching it from here to here, and hold up. Okay. And now we're going to surf again into just a regular website. That website should now be appearing in the list of captures URL. And as Amit mentioned, one of the capabilities of a PAC malware is to prevent access, shut down access to different websites. We call it triggers in our PAC malware. And basically what I'm going to do right now is I'm going to shut down any .com websites using the PAC malware. And going back into our browser, you can see that once I'm refreshing, Blackhat no longer working. You can see it's happening the same for HTTPS URLs. However, trying DEFCON, you can see that it's working. Amit, back to you.
Thank you, Itzik. To summarize, we've seen an unorthodox installation, PAC only, makes it a bit harder for antivirus products to detect it. We've seen that PAC malware is capable of, depending on the browser, HTTPS URL interception, denial of service, and distributed denial of service. And we've discussed the fact that we have a two-way command and control protocol via DNS with a flexible execution via eval. Now, here is a matrix describing how various browsers implement various PAC features. You can see more or less we've touched all those topics, but in the top left corner we see Internet Explorer 11 and Edge and Internet Explorer and Microsoft Edge. They do not have file support by default, but we can turn it on in registry. And find proxy for URL invocation frequency is by default trimmed, but we can set it up as the full URLs again by registry settings. The Safari items and iPhone for find proxy for URL invocation are trimmed at this moment, but earlier this year they were providing full URLs, so this is pretty fresh. Note that we report on Chrome 51, but in Chrome 52 2 weeks ago the URL is again trimmed, and Firefox we report on 4701, but we have not tested yet 48, which was released yesterday. The DNS resolve bug line at the bottom is interesting. We noticed that in all Internet Explorer, in all Microsoft browsers, there's a funny bug. If you invoke DNS resolve without using the result in any calculation, it will throw an exception. This is why we needed to add an empty string to the DNS resolve result in the malicious PAC example. So let's discuss ideas for remediation and fix. Remediation first. At the user level, we suggest disabling WPAD in untrusted networks, or in general if possible. If you do need to access an untrusted network, we propose that you use a browser that exposes as little as possible of the URL to find proxy for URL, that is, trimmed URLs. At the corporate level, we suggest avoid using WPAD, which will allow the corporate to turn off WPAD in all the browsers and machines. Server side, we suggest removing security-related data or tokens from URLs when possible. It's not always possible, of course, but when it is, it's a good idea. Also, to move away from HTTP authentication, assuming that it is under TLS in the first place. So in general, using sensitive data inside URL is not a good idea. As for a more robust fix, we call upon IETF to fix a WPAD semi-standard, and to turn it into a standard, by the way, and force a secure PAC retrieval wherein the client identifies or validates that the PAC is genuine and is provided by the genuine network operator. Of course, over and using a transport in transit security. Right now, this is not mandated. And to standardize the PAC, maybe trim the URL to host only, or deprecate DNS resolution. As for browser vendors, we propose restricting the PAC functionality by trimming the URL and disabling DNS resolution, and some browser vendors indeed started walking this path. To conclude, what we saw here in general is that interception of HTTPS URLs has some serious security consequences. We talked about credential theft and session hijacking and in general loss of privacy. Additionally, PAC in general can do phishing by invoking alert, and denial of service or distributed denial of service. Specifically to the remote scenario, trusting a PAC retrieved in the clear from an unverified external source for handling secure, meaning HTTPS traffic, is a problematic concept. We believe that this is the root cause for the HTTPS exfiltration problem. The remote scenario is also, note that the remote scenario is also difficult to detect locally by antiviruses and so forth, because it leaves very little footprint on the machine. The PAC malware scenario is an unusual malware persistence, which is not necessarily detected by all antiviruses. Still, it's a very powerful concept. It can even obtain more than the remote attack, because we can tweak the registry to provide more information. It's now time for question and answers, but we also remind you to fill the feedback form.